The goal today is to talk about inverse functions, and in particular, how they relate to derivatives. This can be an important topic because some functions are best understood as inverse of other functions. So, for example, the natural log function is the inverse function of e to the x. Well, we understand e to the x, so what we'd like to do is take our understanding of one function and transfer that understanding to another function. So in our case, can we take the derivative of e to the x and use that to figure out the derivative of natural log of x? Well, yes, we can. So let's get into it and see what happens. So the first thing for us to talk about is a refresher of inverse functions. So we have a picture here to help us. So imagine you have a function y equals f of x. Then the inverse function would be the result if you flipped it across the line y equals x. So this is what the graph of f inverse of x looks like. Now, not every function is invertible. So if you think back to what's known as the vertical line test, well, a vertical line test says if you have some function, say for example this function, this is not a function, right? What's the problem? Well, the problem is if you draw a vertical line here, you're going to hit in two locations. And the basic principle about functions is for any input, you should only get one output. So the fact that we would have two outputs associated with a particular input says not a function. So that's the vertical line test. That helps us figure out whether something is a function or not. The horizontal line test says the following. If you have some curve, if you can draw any horizontal line, and if it hits multiple times, then the function cannot be invertible. The problem is, what value is the right thing to associate with the inverse? Because when we're talking about the inverse, what we want to say is, what input should we get to produce a certain desired output? So I want to produce an output that corresponds to this height, this dotted line. And the horizontal line test, if you hit multiple times, says, well, there are multiple candidate inputs. So that's the horizontal line test for telling whether or not a function is invertible. Now, the big idea to drive us forward geometrically, and we're going to do this both geometrically and algebraically, so you can actually do it in both ways when we talk about figuring out what's happening with the inverse, is to think about what's happening with the points. You see, we're flipping across the line y equals x. So we're doing this sort of motion here. What that translates into is if you have a particular point here, let's say that's at the location a comma b, when you flip across the line y equals x, what happens is you interchange what y and x do. So you end up at the point on the other side is b comma a. So that's how you can see where things map back and forth. And if you think back to algebra, one of the things that you often did when you're trying to find an inverse of a function was this idea, well, if I have y is equal to some function of x, so y equals f of x, you would swap x and y, so then you have x equals some function of y, and then you try to solve for y again if you could. Sometimes you can, and then if you can, well, that's the inverse, and sometimes you couldn't. Well, see, that's that swapping rule. AB going to BA. Now, for our purposes, we're after understanding derivatives. And if we think about what derivatives are, well, derivatives can represent slopes of tangent lines. So we can ask ourselves the question, well, what happens to a tangent line? So I can imagine I come, say, to this point. I'll pick this one because it's an easy point to pick. Nothing special about crossing the axis. Well, there's a tangent line to that point. Here it is. Now, what's going to happen? Well, when I flip this point across, I'll come down here, and there'll be a tangent line to this point. And lo and behold, what will happen is that the tangent line will carry along with the flip action. So as you're flipping the curve f of x to get the curve f inverse of x, the tangent line at this point will pick up and carry over and become the tangent line at that point. So that's going to help us figure out what's going on. So here's where we're at. If we have the following. So we have this line y equals mx plus b is tangent to our original curve at some point. Okay, then we flip over, what happens? We swap the role of x and y. So instead of y equals mx plus b, we get x equals my plus b. So now that's tangent to the new curve, which is the inverse function. But at what point? Well, you swap a f of a, so you go to f of a comma a. Okay, now a little bit of algebra here, not much. Since we have x equals my plus b, let's rewrite that so we have it more in a form where we can see the slope. And what do we see? Well, what we can see is that our slope becomes something kind of nice. See, if our original slope is m, then the result of flipping across the line y equals x, so that turning over motion produces a new slope of 1 over m. So in other words, it's the reciprocal. It's not the negative reciprocal. See, negative reciprocal, that's what we do when we want things to be perpendicular. That's not the case here. It's not that we want them perpendicular. But what happens is a 1 over action. All right, so we're almost done. See, we now can carry through the process. So we know the slopes of the function and the inverse are related by these 1 over. There is the one caveat we have to say, but wait, the location has changed. And what we mean by that is if you go back here to the previous page, you see this location is, the input, the x coordinate, is different from that location. Okay, so now we say, aha, so we have a tangent line. At some point, it becomes a new tangent line, so there's a derivative there, becomes a new tangent line, and that tangent line has a slope of 1 over the original slope, but we have to account for the new location. And how do we all put it together? And here's the answer. So if I'm after a derivative of the inverse function at some point x, can be any point I want, then it's 1 over the derivative of the original function, but not at x, but what you would get if you did your flip. So in other words, you were to exchange, and that means that you evaluate at f inverse of x. Okay, so there's our rule. So the derivative of f inverse of x is 1 over f prime of f inverse of x. Good, good. Whew. All right, now, if you don't like the geometric picture, let's talk about the algebraic approach. And really, what we'll do is build off of what we did in a previous session, which is implicit functions. So here we go. We know we are interested in the curve f inverse of x. So we have y equals f inverse of x. So we want to get to something that we're more comfortable with. We're comfortable with the function f. So we want to get rid of the f inverse. So we say, okay, so the way to get rid of the inverse function is you apply the function f to both sides. So really what's happening is that this x here corresponds to f of f inverse of x. And what you do is when you take f of f inverse, what is that asking you? Well, the inverse of x says, what do you have to plug into the function f to produce an output of x? And then you say, okay, well, whatever you have to produce, that's what we're now going to plug into f. And therefore, the output has to be x. So in some sense, the function and the inverse, they undo each other. If you think of it in terms of that flipping, if you flip once and then twice, you get back to where you started. So that's why we think of the f and f inverse. You get back to where you started. Now we say, all right, these two things have to be equal, therefore their derivatives have to be equal. That's not so bad. So we take their derivative. On the left-hand side, we use the chain rule. So the derivative of the outside, f prime, leave the inside alone, times the derivative of the inside. Well, that's the derivative of y with respect to x. On the right-hand side, we have the derivative of x. Well, that's 1. All right. Well, move the f prime of y across. So dy dx is 1 over f prime of y. And now we know dy dx is just another way of saying of take the derivative of y. So that's what we mean when we say dy dx. It says what happens when you take the derivative of y. Now the last thing for us to do is simply say, Well, what is y? We know what y is. It's f inverse of x. So we can put an f inverse of x there as well as there. And therefore we get that the derivative of f inverse of x is 1 over f prime of f inverse of x. And we're done. All right, good. Now, you might wonder, how do we use this? Well, there are some functions which have nice inverses, and we'll actually go through a couple of them, at least one today and some more in a future session. But sometimes what we do is we say, well, I don't know how to find the inverse function. In fact, finding the inverse function can be very challenging, if not impossible. And of course, we don't want to do impossible things. We always like to do things which are possible. So we say, okay, what if I want to find the derivative of the inverse at a particular point? All right, well, can we do that? And the answer is, well, yes. See, if I want to find the derivative of f inverse of x, but at a particular point, x equals a, what we're really saying is we're looking at 1 over f prime of f inverse of a. And the good news is f prime is, generally speaking, pretty easy to compute because we know how to find derivatives of functions, and our function is usually not so bad to take a derivative of. So the real trick comes from saying, all right, if you can figure out what this is, what f inverse of a is, then you're usually good to go. So it reduces the problem to saying, what's the inverse, f inverse of a? Now, I want to mention that there's a really good strategy, which a lot of people feel is not an appropriate strategy to talk about in math, but it really is a good strategy in math. And this is called guess. Actually it's called guess. In other words, if you're not sure, try some values, because we don't always have to find the whole inverse function. What we need is, if we're after the derivative at a particular point, we have to say, okay, well, we just need to figure out what's a value that produces the right output. So in other words, look at the function f and ask the question, well, what do I need to plug into my function so that the output equals a? If I can answer that question, that's what f inverse of a is. Now, you might think that guess is not a very good mathematical technique. It's actually a beautiful mathematical technique. One of the ways I like to think about differential equations is that a significant chunk of differential equations is I'm going to guess an answer, and I'm going to be wrong, but by examining my guess, I can see how to modify it so that I'm right. And so you get to learn the method of good guessing. And well, it turns out that with practice, you can get good at guessing. It does get better. All right, now I promised that we were going to talk about natural logs, so now let's transform and go towards that direction. So it's important to remember that the exponential function is very closely connected to the logarithm function in the following sense. If I have my function f of x is e to the x, then f inverse of x is natural log of x. So the exponential function e to the x and log of x, they are the inverses of each other. Now, it might be helpful to recall what they roughly look like. And so e to the x, if you were to sketch that, has the shape that looks vaguely like this, where you come off, and as you head towards negative infinity, you get close to 0. As you head towards positive infinity, you get big. So that says that natural log of x, if you can imagine taking that curve and flipping, what's the result? Well, the result will be something like, I chose a very bad way to draw this, but we're going to come off this asymptote and then head that way. And so in particular, there is an asymptote at 0. So as you head towards 0, you're going towards negative infinity. Just as here, as you head towards negative infinity, you head towards 0. The other thing to note is that as you head in the positive direction, natural log of x will head off towards infinity. But it does so very grudgingly, in the sense that it grows slowly. So natural log will head off to infinity, but it'll drag its heels as much as possible. So it grows very slowly, much slower than, for example, x to any positive number, so x to the 0.01. Natural log of x grows slower than that. All right. Now, we have some nice properties for the exponential functions. So, for example, if you take e to the a times e to the b, you add the exponent, so e to the a plus b. That translates into natural log, saying natural log of a times b is natural log of a plus natural log of b. In other words, you can transform multiplication into addition. Now, nowadays, it doesn't seem like that's such a big deal, but that was a huge deal, because if you have to pick between doing an addition problem or doing a multiplication problem, you would always pick addition. Addition is a much cheaper thing to carry out. And so you say, okay, well, why is that important? Well, back in the day, we didn't have computers. And so we were like, well, if I'm doing all this computation, I want to do the cheap computation, and how can I convert my expensive multiplication to my cheap addition? So step in slide rulers. Now, most of you are probably too young to ever have heard of slide rulers. You probably have never even seen one. But if you ask your parents or grandparents or maybe even great-grandparents, probably your parents, but anyways, if you ask them, they'll talk to you about, yeah, there was this little thing that you would slide back and forth, and what it would do is it was essentially built-in logarithm, and it would help you to carry out and say, hey, I can use this to transform multiplication to addition, and therefore I can do computations much faster. And of course, taking logs does many other wonderful things. Let's just talk about some more. We don't want to get too hung up because there's lots of beautiful properties. So for example, if I have e to the power a, that raised to the power b, that's e to the power a times b. Well, that translates into logarithms as log of a to the b power. The b comes out in front. So b log of a. All right, so that says, hey, I can bring exponents down very easily. So bringing down exponents is now super easy with logs. Wow, cool. If I do division, e to the a over b, that is e to the a minus b. Translation, log of a over b is natural log of a minus natural log of b. Because they're inverse functions, and remember we said inverse functions undo each other, we get log of e to the x is x, and e to the log x is also x. Now there's this little caveat which says as long as x is positive. The reason there's that caveat is you'll notice that the natural log of x is only defined for positive values. You cannot have a negative input into your logarithm, just because you cannot have a negative output from your exponential function. A few other quick facts. E to the 1 is e, and e to the 0 is 1. So that translates into log of e is 1, and log of 1 is 0. Now, I often say log for natural log, but natural log is the best log. And why is it the best log? Well, it's the best log for the following reason. Let's run this through. So if y is the natural log of x, then x is e to the y. So we're doing that sort of switch the roles in implicit differentiation. So derivative of x is 1. Derivative of e to the y is e to the y times y prime, which is, of course, a fun way of saying, dy dx. We say, aha, e to the y is x, and therefore we come to the really beautiful answer. The derivative of the natural log of x is 1 over x. Wow. Now this is a really important derivative. The fact that it's boxed, it just does not emphasize just how important it is. So we're going to put some extra boxing here, just so we can remember. This is one to really know, because log shows up very, very frequently, and it's an important function to know and to use. And in general, you really should understand the properties of logs very well. And I want to draw attention in particular to these three properties right here. These you should be completely comfortable with using. Namely, natural log of a product turns into addition. Log of a to a power, you can pull the power down. Division becomes subtraction. These you want to be comfortable with because they're going to help you rewrite. Word of warning. Sometimes people try to get logs to be too good. So logs work great when you have multiplication. They do not work great when you have addition, which is to say log of a plus b is definitely not log of a plus log of b. So in other words, it does not break up well over addition. Don't try to do anything fancy with addition. Okay, keep that in mind. A couple more things, and first off, we've often talked about the derivative of e to the x, and we said, hey, the derivative of e to the x is really nice, it's e to the x. You can really have any number downstairs. So a, we're thinking of that as a constant. So the derivative of a to the x, well, what do we want to do? We want to reduce it to something we've done before. So we want e to something, because we know how to handle e to something. So we can say, well, hey, a is e to the log of a. Now, how do we know that? Well, we are basically using this fact here. So, oh wait, no, this one right here. Here we go. So here we have a is e to the log a. Okay, so e to the log a x. All right, well, e to the log a raised to the x power is the same as e to the log a times x. How do we know that? Property of exponential functions. So now we're ready to take the derivative. We haven't actually done a derivative, we've just rewritten. Now when we take the derivative, well, the derivative of e to something is e to that something times the derivative of the upstairs. Well, it's the derivative of a constant times x, which is the constant. So that's where that log a is coming from. It's coming from the chain rule. And then finally we say, hey, that e to the log a of x is a to the x. So note, why is the e to the x function so nice? Well, it's because log of e is 1. And log of any other number besides e is not going to be so nice. And so that's why we like working with e to the x. It's the same reason why we like working with natural log. You see, if it was any other log besides natural log, so in case you're wondering what I mean by any other log, so natural log is sometimes written as log base e. You can do log to any base. If it's any other type of log, you'll get a constant showing up. And we'd like to avoid that if possible. One last thing here, before we talk about our last idea, is that we can apply the chain rule. So the derivative of natural log of f of x, well, remember, you take the derivative of the outside. The derivative of the outside is 1 over. So the derivative of log, you should always think of the derivative of log as being 1 over. So it's 1 over, plug the inside in, so it's 1 over f of x times the derivative of the inside, which is f prime of x. So this is the chain rule mixed with the derivative of natural log of x. One more topic to talk about for today. And it's a wonderful, beautiful topic. It's called logarithmic differentiation. And it sounds very complicated, but when it comes to differentiation, it's not introducing any new tools. What we mean by logarithmic differentiation is we say, hey, logarithms have this wonderful way to simplify expressions. And so in particular, if I have a bunch of stuff multiplied together, I can use logarithms to pull it apart. Or if I have something downstairs and something upstairs, I can use logarithms to pull it down. So in other words, I can turn multiplication into addition, and addition is much easier to work with because it says when I'm taking derivatives, do the individual parts. And when I have something both upstairs and downstairs, it turns it into a product rule, which again, that's something that we can handle. So when we use the word logarithmic differentiation, it means I want to take the derivative of something complicated, but if I apply the log to my expression that I'm taking the derivative of, it simplifies to something easier and something which I could take the derivative of. And therefore, what we'll do is take the logarithm, use the properties of logarithms to simplify, and then we'll take the derivative. And then, of course, we have to keep track. Now, here's how it works in practice. Suppose I have the derivative of some function f of x. Well, that's f prime of x. So that becomes f of x times f prime of x over f of x. You'll notice here the 2f of x is canceled. And this expression we just saw, That's what we got when we took the derivative of the natural log of f of x. So here we go. This is logarithmic differentiation in a nutshell. If I want to take the derivative of any function, that's equal to taking the function times the derivative of the natural log of the function. So how can we use it? Well, suppose we asked you to do something like take the derivative of, I don't know, let's say x squared plus 1 to the power sine of x. Now, that's not so clear what to do, right? Because we haven't encountered anything like this. You see, the downstairs is changing because that has an x involved. The upstairs is changing because it has an x involved. So it's a lot of stuff is changing. But the idea here is to say, hey, if we apply the rule that says rewrite the function x squared plus 1 to the sine of x times by the derivative of the natural log of x squared plus 1 to the power sine of x. All right, now, so far it doesn't seem like we've gained much, but we have gained a little bit because we can use the properties of log. And in particular, the sine of x term here can come down. So again, the logarithmic differentiation, the logarithmic is just saying, hey, by using properties of logs, you can make things simpler to work with. So you end up with sine of x times a natural log of x squared plus 1. So now you have, say, something that's easy to work with in the sense that we recognize it. It's a product rule, and we have a rule for that. So whereas this doesn't look like anything we can take a derivative of, this looks like stuff we can take derivative of because I know how to take derivative of sine, and we just learned how to take derivative of natural log. So woohoo! Progress! We can make progress. So when do you use logarithmic differentiation? Well, basically, you're going to use it in two cases. So the first case is when you have a function to a function. All right? In that case, you have to use logarithmic differentiation. You have to pull that upstairs function down. So that's the first case. The second case is when you have a lot of products of functions. And you can get by without doing logarithmic differentiation in that case. In other words, you have a whole bunch of pieces multiplying together and you want to take the derivative. It's not required to do logarithmic differentiation, but by taking the log, the product, and by the way, when I say product, I include division, says, hey, break up into the sum of lots of little pieces. And now it's like, oh, now I have a lot of little tiny pieces and each one is very comfortable to work with. Life is good and I can make progress. All right, cool. Well, that's logarithmic differentiation. Now, I will point out that you can actually do a lot of good stuff with logarithmic differentiation. So let me point out two kind of interesting facts. So I have a little bit, I'm going to move up into the top here. So recall that we said that the derivative of x to the k is equal to k x to the k minus 1. But we only proved that when k was a whole number. When it's not a whole number, we didn't prove it. But now we can. So here we go. We can use logarithmic differentiation. So this is the original function, which is x to the k, times the derivative of the natural log of x to the k. Now what happens here? Well, I can use the properties of log to pull the power k down. So this is x to the k times the derivative of k times natural log of x. Well, k is a constant, so that would come out. So you would get k, x to the k, and then the derivative of natural log of x is 1 over x. And now you see, hey, it's x to the k, 1 over x, and that is x to the k minus 1. Woohoo! Nice! Good. Progress. Progress. Now, can we do anything else? Yeah, we can. Now, watch this. Suppose I want to find the derivative of f of x times g of x. This is the product rule. Well, okay, so according to Logarithmic differentiation, you just write down what's on the inside of the derivative, so that's f of x, g of x, times the derivative of the natural log of f of x times g of x. Okay, so far so good. I'm just applying the rule. Now, let's use properties of logs. Properties of log says, hey, I have a product that becomes addition. So that's f of x, g of x times the derivative of, and I haven't taken my derivative. In fact, oftentimes, most of the work with logarithmic differentiation is working with simplifying the expressions involving the logarithm, so way before any derivative happens. All right, now let's take our derivative. So this would be f of x, g of x, the derivative of natural log of f of x. Well, the derivative of natural log of anything is what? Well, you put the anything downstairs, so it's f of x, and the derivative of the inside, so f prime of x. So think of the derivative of natural log as 1 over. So 1 over the inside. So that's why you get the inside downstairs, derivative of the inside from the chain rule. Same thing here. 1 over the inside. So there's a g of x downstairs, derivative of g of x upstairs. And there you go. Now, watch. Multiply it through. On the first term, the f of x's cancel. So you're left with f prime of x times g of x plus, in the second term, the g of x's cancel. So you're left with an f of x times g prime of x, which is a product rule. So once you understand the derivative of natural log, and you understand the chain rule, the product rule is a freebie. You get it without a lot of work at all. So, well, it's actually really powerful. Logarithmic differentiation. Good stuff. But of course, to make it useful, we've got to practice. So I think it's time for us to start thinking about doing some practice. Good. All right.